Hello, in this video I will go over some differential equations terminology. So we're going to start off by defining the difference between ordinary differential equations and partial differential equations. An ordinary differential equation, which is sometimes called an ODE, is a differential equation where the unknown function is in terms of one independent variable. So examples of ODEs would be all of the problems that we have solved up to this point in the class have been in terms of one independent variable. They've been in terms of t. An example would be a differential equation for finding the electrical charge on a circuit. So this is an example of such a differential equation. So it's a second order differential equation. We'll get into order a little bit later, but we will cover this, how to go through and derive this equation later in the course. It is the equation for going through and finding the charge on an electric circuit. So by comparison, partial differential equations which are sometimes referred to as PDEs, are differential equations where the unknown function that you're trying to find is in terms of two or more variables. So some examples for that could include the heat conduction equation, which is the following. Another example would be the wave equation. These are both pretty famous. So the heat conduction equation is for going through and modeling conduction of heat in a solid object, and the wave equation is for going through and modeling wave motion in either solids or fluids. Okay, so just to kind of compare these two when they're sitting side by side, the difference is that in one case we have one independent variable, and in the other case we have two. All right, so you notice we have t, it's inside the function for q, here, here, and here. So there's just a single independent variable. Okay, meanwhile, if you look at the functions here, they have x and t. All right, so here we've got two independent variables, two inputs into our function. Here we have one input. One input is an ordinary differential equation. Two inputs is a partial differential equation. So this course is on ordinary differential equations. If you're interested in partial differential equations, then you'll have to take another course in differential equations. Okay, the next thing we're going to look at are systems. If a differential equation has more than one unknown function, then it is a system. So of course, it also has to have more than one equation as well. So if you have more than one unknown function and you have more than one equation, then you have a system of differential equations. It's the same basic definition that we have for going through and solving a system of regular equations, linear equations. If you have more than one variable and you have more than one equation, then you have a system of equations. So an example of a system of differential equations would be the Lafcaterra predator-prey equation. And that equation is given by So you'll notice that we have two equations and we have two unknown functions. You have one unknown function is x. So we're trying to find the function x that we'd plug in that would solve the differential the system, and we're trying to find the function y, right? So the solution here, again, is just like with all the other differential equations. It's not going to be a number, it's a function. So there's two functions are what we would plug into a system of differential equations to make that system true. And in this case, it's going to be the function x and the function y. So x of t models the prey, the population of the prey. And y of t models the population of the predators. And we will solve systems of differential equations at the end of this semester. Next, order. The order of a differential equation is the order of the highest derivative. In the equation. So for example, if we had y triple prime plus 2e to the t y double prime plus y prime equals t to the fourth. If we looked at this, we would say we've got a third order, third derivative, a second derivative, a first derivative, and so the order of the differential equation is 3. One more thing that we're going to need moving forward is that typically differential equations are written in one of two formats. Well, one of three formats, really. But in terms of general representations, we either have all of the functions are on one side, or you have the highest derivative by itself, and then all the other functions are on the other side. I say one of three forms because this is also a format here where you have the function that does not contain the dependent variable, right? The function that's just in terms of the independent variable is on one side, and then the functions that contain, that you're trying to find, the unknown function that you're trying to find, is all on the other side. So essentially, it would be this, except you would take the t function and you move it over to the other side. So that's really the three different formats. Either you have y of n by itself, and then the rest on the other side. You have everything on one side, or you have everything on one side except for the t function, which has been moved to the other side. That's what we have here. Okay, next. We have linear and nonlinear differential equations. A linear differential equation is a differential equation that has the format that we just talked about. If the function f here that's defining this is linear in the variables y prime, dot, 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 through yn. And note, it's y through yn, so t is not included. So a differential equation is linear if this function here that defines its structure is linear in the variables y through yn, and again, t is not included. So what does that mean? If you're not certain, or if you're not certain of what it means to be linear, linear just means that a function is linear if the thing that it applies to is to the first power. So what it's saying is that all of these variables all have to be to the first power, and they can't be multiplied together, right? If you think about a linear equation in an algebra class, we would say x plus y equals 4 is a linear equation. Why is it linear? It's because x is to the first power and y is to the first power. If you have xy equals 4, this is not linear. You can't have the two multiplied together. And if you had x squared plus y equals 4, this is also non-linear. So to be linear, everything has to be to the first power and not multiplied together, okay? And so these are both nonlinear. And the same thing applies here, okay? But again, t is excluded, so it only applies to the unknown function that we're trying to find. So in this case, the unknown function is represented as the y. So it just means that the y's all have to be to the first power, and they can't be multiplied together. Thus, knowing that, we could go through and represent a general linear differential equation has the form So here's the general format, and you can see we have y of n. It's to the first power, right? So this is the nth derivative. Don't get confused and think this is an exponent. This is the nth derivative, and it's to the first power. Nth minus first derivative to the first power, through y itself to the first power, and then the excluded thing could still be a function, and that's g of t. So g of t does not have to be to the first power. This could be sine of t or cosine of t or t squared. All of those, this would still be a linear differential equation. Okay, so again, y through yn have to be to the first power, and they cannot be multiplied together. that is what is required to be a linear differential equation. What about nonlinear? A differential equation is nonlinear if it does not satisfy the requirements to be linear. Okay, so what is the opposite of all of these having to be to the first power and not be multiplied together? Well, one or more of them is not to the first power, or there is a product of two of them. So that would make it so that it's nonlinear. All right, so not to the first power, or not, or you have a product of any two of these. So an example, the oscillating pendulum problem is a classic example. The oscillating pendulum equation is given by d squared theta dt squared plus g over L times sine theta equals 0. All right, so why would this be nonlinear? Well, if you look at it, the unknown function that you're trying to find is theta, are all of the thetas to the first power. So this is the second derivative, and it is to the first power. However, this one is not to the first power. It's inside of the sine function. Okay, so if you had g over L times theta, not sine theta, then it would be linear. But the sine here is what makes it so that it is nonlinear. Okay, and finally, solutions. The solution of an ordinary differential equation in the interval alpha to beta is a function delta such that delta prime, delta double prime, dot, 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 through delta nth derivative all exist and satisfy the equation so there's a lot of complex language in there. Let's just check what this is saying. So this is saying that we have a function that is defined on an interval, and you could go through and take the derivatives, and all of the derivatives also are defined. They also exist. And so you have a function and its derivatives, they all exist, and then you went and took them and plugged them into the differential equation, and it satisfied it. It made the differential equation true. So this word satisfy, that's just what it means. So it's the same definition that we've been using up to this point. A solution to the differential equation is the function that, assuming you're talking about existing on an interval, that exists on an interval, that if you plugged it into the differential equation, it would make the differential equation true. And the only way that's going to happen is if the derivatives all exist and the function itself exists on an interval. Okay, and then the last thing that we're going to cover today is that when we're talking about functions that we're trying to solve, f, typically f is real valued and phi is real valued. So the function that we're going through and solving is a real valued function, and the solution that we end up finding is also a real valued function. That is typically going to be the case in this course. Okay, so that is it for our section on some basic definitions. Thank you for watching, and I'll see you next time.